Okay, class, this is the quick simulation about the kinetic molecular theory. What we have here, I want you to notice, is a simulation from the PhET, P-H-E-T, which you can log on yourself. In fact, if I can move this down, there it is, P-H-E-T. You could log on as a student and get an account and do some of these simulations. What I want you to notice is a couple things. First, look at the different molecules. This is neon that's currently in here. I could put argon in there. I could put oxygen, which is diatomic. Remember, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Or I could put a water molecule in here. And we're going to go through the different states of matter. So I'm going to go back to neon. Notice at the top here, the temperature is in kelvins. And we can add heat by rolling this up, or we can cool it off by just moving this up and down. And we're going to see what happens. Now, the kinetic molecular theory says that solids are rigidly shaped. They have a fixed volume and a fixed shape, and you know that's true. Your calculator is a shape like a calculator, and no matter what you do, it's shaped like a calculator. It's a solid. I can't pour the calculator out. Now, if I add heat to something, notice first of all this solid of neon, all the molecules are wiggling and moving because everything's moving. Everything has kinetic energy. If I add heat to this, though, the temperature is going to begin to go up at the top. Now it's, look here, it's 26 kelvins now. The molecules are gaining more heat energy. They're moving more. They're moving more rapidly. If I keep adding heat, they're going to get more and more energy until they start to act like a liquid, okay? And liquids are able to flow, and some of them get enough energy they fly off. Okay, so let's look at a liquid. A liquid, it doesn't have a fixed shape. It has a fixed volume, the same number of particles, but the shape is going to change as you add the energy to it. And if you add even more heat, that liquid, all the particles in there get more and more kinetic energy until they have enough energy to break apart from each other and fly apart and fill up the container. And so eventually you have a gas. And when you have a gas, all the particles are flying randomly and hitting containers, and they're filling up the entire container. So a gas has no fixed shape and no fixed volume. In fact, if I open up a container, all of the gas would fly out and start to fill in the bigger container. So let's go back to liquid. No fixed shape, but definitely a fixed volume. It's not going to get bigger than this. It's just going to, squash and reshape, but it's always going to be this size. Think about filling up your Coke or your water into a water bottle, pouring that water out onto the desk. You still have the same amount of water, but now the shape of the water changed. A solid has the fixed shape. You have a cube of ice. It's a solid. You pour that cube of ice onto the table, you still have a cube of ice sitting on that table. It had the same shape and the same volume. Liquid, same volume, different shapes. Gases, no fixed shape, no fixed volume. And what's the difference between them? When you add heat, you increase the kinetic molecular energy, so the particles don't stick together well anymore, and they start to pull apart. They have enough energy to get away from each other and fly apart and fill up their container. So we can also do argon this way. There's argon as a gas, as a liquid, and as a solid. And water molecules are interesting. There's the water molecule as a solid. You can actually see that the solid water has these little spaces in between them. But liquid water, notice how it looks a little bit closer together. Liquid water actually becomes more dense because even though they're wiggling and moving around more, they don't have those big spaces. And we'll talk about why that is a little bit more later. And then gas water fills up the entire container. Notice that each time the temperature is going up for each one. Okay? Now, remember, okay, I'm going to cool off my water now. Now, it's not that the ice is adding coldness. Remember, heat flows from the hot to the cold. So they're bouncing into the ice, and their energy is flowing into the ice, and that's cooling it off until they're eventually going to reform the solid shape. Okay? All right, that's how you use this simulation. I hope that's helpful.